So Poisson distribution or random variable. And so this is just a kind of a generalization, not generalization, maybe limiting case of a binomial distribution. So remember that the binomial distribution, binomial random variable, we have n trials. So you can think about something like these are trials. So trials. And there was n of them. And the probability that you find something in which trial that will be success in this trial. You can think about it looking in a boxes with n boxes, and the probability that you'll find something in a box is equal to p. Right? So these were parameters of this distribution. So now then here x is a number of successes, and so the number of balls found in these boxes. And well, kind of it has a probability mass distribution function, which was this was k out of n, pk 1 minus p to the power of n minus k. And so this was just found by combinatorics, right? So we counted the number of, not exactly by combinatorics. N of k was found by the combinatorics, and this p times 1 minus p in the right powers was found by using this independence assumption, right? So now we also found that expectation of x, so expected number of x, was equal to np. And so now when we go to Poisson random variable, so this is kind of so the number of these boxes becomes infinite, right? So this is imprecisely speaking, right? So imprecisely speaking, the number of these boxes becomes very, very large, but kind of infinite, right? So so you can think about every point here as a box, right? So infinite number of trials. So n is equal infinity. And so now the probability that you'll find that that there is a box or something happened in this specific moment is very small. And so you can think about that this probability is effectively equal to 0. And so now the question, well, okay, so this is a limiting case. So n is very large. So you can think about it as infinity. P is very small. You can think about it as equal to 0. And so can you say something about this situation? And so, but you still want to know what's the number of the successes. It's still number of some events that happened during this, say, period of time. So you can think now about every point as a point in time, and you want to figure out what was the number of the successes. So we had an example when there was a counter that counted particles, and every time when a particles enters a counter, there is a kind of impulse. And so you can see an impulse. So you want to know how many particles enter the counter for this specific interval of a time. And then you can think about this, okay, so there is p is equal to 0 and is equal to infinity, but you can think about that expectation of x. It's not infinite, not 0, it's equal to some number lambda. And so this you fix about. So this will be a parameter. So a parameter of a distribution. Before that, you have two parameters, n and p. Now you have n is infinity, not useful. P is equal to 0, not useful. But their product is equal to lambda, some number which is kind of, well, useful. Right? And the last time what we did, very kind of quickly, we found out that you can figure out what's the probability mass function as a limit. So we took this probability mass function and took the limit when n goes to infinity, p goes to 0, but their product is fixed. Okay? So we found that in this case, turns out that the limiting, there is a limit. So this is also surprising. There is a limit, and it's given by this unusual formula. So it's equal to E. So from natural logarithm, so E, which is kind of number 2.7 something to the power of minus lambda. So this is a constant, E to the power of minus lambda. It doesn't depend on K. And here the thing which depends on K. So it's lambda to the power of K divided by K factorial. So this looks kind of unusual, and so it enters with E, which is, well, just happened to occur here, kind of. So now this is a PMF of the Poisson distribution. And it's very surprising that you have something like the one distribution for every situation. So it doesn't matter kind of what you count. You can count the number of the particles which enter the registering camera. You can count the number of typos on a page in a book, or kind of you can count the number of server requests that some computer server obtains in a unit of time. You can count number of galaxies in the universe, something like that. So at least in the first approximation, it will be Poisson. Right? So now not always. So kind of it happens that it's Poisson. There are some assumptions which we made about independence. And so if you observe one occurrence, so in some specific point, the assumption is that it doesn't influence that you observe in the next observe another occurrence in the next point. So it doesn't influence probability. So if it's violated, then the Poisson distribution is not realized. Then the distribution of the successes on this infinite line is not Poisson. So this says that if you have some clustering in the data, then there is some deviation from this Poisson law. From this, so this is kind of Poisson law. Poisson law for probabilities. So if you have a clustering, so violated if there is some clustering. And by clustering means exactly the deviation from the independence of each observations. Clustering. Right. So, well, kind of, we will not look at this, but if you kind of analyze the real data, then you will know that, well, in first approximation Poisson, if there is some clustering, you'll need to modify it somehow. Right? So there are more complicated modification which is studied in statistics of the point processes. Right? So okay, so this is the law. So now what we can say about this? Okay, so we derived it by using some limiting procedure. So it's also kind of useful to check whether it's really a valid PMF. Right? So kind of the claim is that this star is a valid PMF. Valid PMF, which means that we'll need to check that the probabilities are non-negative, and it's obvious that they are non-negative. These are all positive. These are all positive numbers. And the second thing that you'll need to check that the sum of the probabilities is equal to 1. So you'll need to check that the sum of the pxk over all possible values of k. So now all possible values of k, maybe it should be kind of specified. It's always useful to write down for which values it's true. It's true for k is equal to 0, 1, 2, and so on. Right? K can be 0, no occurrences, 1 occurrence, 2, and so on. Right? It cannot be negative. So you look at the sum from k is equal to 0 to infinity. Well, you need to check that it's equal to 1. Right? So if you write down it, what it looks like. It will be just this sum, so it's sum of e minus lambda k factorial. That k is equal to 0 to infinity, or this doesn't depend on k, so you can take it outside. It would be e minus lambda, and instead of writing this as a sum, right, so you can use in a usual kind of notation just to look at it. So if k is equal to 0, right, so you'll have lambda to the power of 0 divided by 0 factorial, so it's 1. Lambda to the power of 0 is 1, 0 factorial is 1, so 1 plus second term will be when k is equal to 1. Okay, so lambda to the power of 1 divided by 1 factorial, so plus lambda. Next one will be 1 divided by 2 factorial. 2 factorial is equal to 2. Lambda squared. Plus next one will be 1 divided by 3 factorial, so 6 lambda cube. Right? And if you look at this in this expression, and if you learn the calculus well, then you know that what is written here is a Taylor series. So this is a Taylor series. Taylor series for a function e to the power of lambda. Then it's just a function for the function e of lambda, where you think about is the function of lambda. So kind of if you calculate the derivatives, right, evaluated at 0, you will find that the derivative is equal to 1 everywhere, and you write down definition of a Taylor series, and you'll find out that this is this thing, right? So, and now one of the theorem in calculus says that the sum of a Taylor series is equal to the function. So kind of your approximative Taylor series of function. So you see that this is, so this sum is equal to e to the power of lambda, right? Because it's Taylor series for this function, so it sums to this, it's up to this function, and you multiply it by e minus lambda, so the result is it is equal to 1. Okay, so we just verified that this is a probability mass function. All right. So now, so maybe before giving any example, also a couple of properties of this. Okay, so properties. Okay, so now, so the first one, well, is usual kind of what's the expectation of x, right? And what is the variance of x? Well, expectation of x is equal to lambda to the parameter, and variance of x is it also turns out equal to lambda. So now, first of all, it's obvious kind of in a sense that when we derived the Poisson distribution from the binomial, we started with the assumption that average number of particles is equal to lambda. Right? So we started with the assumption that e of x is equal to lambda, and well, in the end we should have lambda. Right? And for variance, so we started with the binomial, and we have a np is equal to lambda. And if you look at the binomial, then variance is np1 minus p. And so np goes to lambda, so this goes to lambda. And 1 minus p, p goes to 0, so this thing goes to 1. So altogether it goes to lambda. Right? So it's kind of, and so this is it's argument, so how you can remember this maybe kind of, right? So it's argument. But again, so this was a kind of motivating thing, so that the Poisson distribution is the limit of a binomial model. And then this is pretty convincing that this should be lambda, the expectation should be lambda, and the variance should be lambda. But in principle, you need to prove it from the from the PMF. So in principle, you need to prove it and maybe kind of indicate how you do it for expectation. So just kind of it's not so important, but kind of if you want to do it from the definition, then you write that the expectation of x, right, is equal, okay, so after that we write what is this, it's what's the definition of the expectation. It's sum of all possible values. So here we think about denote values k, so from k to is equal to 0 to infinity. Here you write k, so value multiplied by the probability, so px of k. So it's the same as k is equal to 0 to infinity. K here is e minus lambda to the power of k divided by k factorial. So now you can notice that here's k, and here's k factorial. Right? So very small cancellation here, right? And so you can write that this is equal to the sum. Here will be e minus lambda. You can take it outside, right? So e minus lambda, it's doesn't depend on k. Then you'll have here k minus 1 factorial. And maybe kind of, if you want, it's k minus 1 factorial, maybe you write here lambda to the power of k minus 1 k minus 1 and took one lambda outside. Right? So sum will be here. Okay, so you could start with sum not with 0, but from 1, because k is equal to 0. With sum, in this sum, k equal to 0, it gives you 0 term, right? So you could start it with k is equal to 1 to infinity. Right? And k, it remains k here. No, it's nothing here, right? So I cancel it out. Right? So now you look at this thing and say, all right, so kind of I can change a variable and write it down as a, okay, say lambda, e minus lambda. After that, change variable and say, well, kind of I'm summing not from k to 1 to infinity, but you are summing with k minus 1, which goes from 0 to infinity. And here's lambda, k minus 1 factorial. Right? And this is kind of this thing I've already calculated, just above we calculated, right? So it's this thing is equal to lambda. So you can think about k minus 1 as a variable. So it's equal to lambda to multiply by e minus lambda is equal to 1. So altogether it's equal to lambda. Okay. So because this is exactly kind of a summation of a PMF here. And so now if you want to calculate the variance using this thing, then the trick is that you start with calculating e of x minus 1 as usual. Kind of a trick is always like that. So you do the thing like I did before. So you write that sum is equal to k is equal to 0 to infinity. After that k minus 1. So you can start not from 0 but from 2 actually, right? Because if it's 0 or 1, these two things will be equal to 0. Multiply by e minus lambda k factorial, and do something like similar to what we did right now, kind of because k will cancel out with k factorial, k minus 1 cancel out. So you do this calculation and find out that it's equal to, I think it's, let me see, I did this calculation. So it's equal to lambda squared. And then after that you say, okay, variance of x is equal to, by definition, expectation. Okay, so x squared minus e of x squared, right? Not by definition, but by our formula. But you can write it this way. So you can write it expectation of x minus 1. Right? So this is slightly different than expectation of x squared. But you can add back e of x. Right? So then this is equal. Altogether, this is equal to e of x squared. And subtract minus e of x squared. Right? And this is equal to lambda squared from here. plus lambda from the previous calculation, so this is E of x, minus lambda squared, kind of E of x squared, right? So it's equal to lambda. And so this is, so I skipped this part, but you can kind of easily to check that this is true. So it's the same thing, you take out lambda, instead of taking down lambda, you take out lambda squared here. Okay, so this is how we proved that the expectation and variance in for Poisson distribution, they are equal to each other, kind of, or kind of. So this is kind of very specific for Poisson distribution. Right, so now here's an example, right? So this is kind of the properties of Poisson distribution, and here is this is an example. So example. So suppose there are so how many of them are 2.6 accidents per month on average. And so suppose that this is on some factory or something like that. And so now you can ask the question. So now we assume that this is so assume Poisson distribution. So sometimes kind of it's not given. So kind of in principle it's not given in a real situation, right? So you'll need kind of to assume that this is true, that there is no clustering in the accidents. If you observed accident, it's not likely that kind of you assume that it's not likely that it will be immediately another accident, which is a little bit non-realistic, but still kind of assume Poisson distribution. Right. So then you can ask the question like, what's the one question? It will be something like that. What's the probability to have between 3 and 6 accidents per month? And so amazing thing about this, you just given one piece of information, average number of the accidents per month. And so you can ask the question, kind of, you can answer pretty specific questions about the distribution. What's the probability to have between 3 and 6 accidents per month? And to do that you'll need just kind of to write it down. So what you're interested is a P of that X is greater than equal than 3 and smaller than equal than 6, right? And well, when you think about this, what it's equal to the probability that X is smaller than equal than 6 minus the probability that X is smaller than equal than 2. And so you have this includes all possibilities 0, 1, 2, 3, 4, 5, 6. And so, but you'll need to exclude 2 of them, 0, 1, and 2. And so kind of you subtract the kind of the probabilities of these three things. And so now, and this is, well, kind of you can go either to the table, again, as usual, you can go either to the table or to some software. So if you want to use some software, then in R, it will be just given by something like that. So it will be P Poisson. And after that, so we can kind of actually kind of, let me kind of maybe, something like a P Poisson 6, and you can say, I think that the parameter here, so parameter lambda equal to 2.6 minus P Poisson. And so this is a kind of, this is exactly the function which calculate this thing, CDF, right? Minus P Poisson of 2 lambda is equal to also 2.6. And so this is kind of one possibility. Another possibility, I think, is to go to the table and calculate these probabilities. And well, in principle, this is a small example. So in principle, you can just write down what's this probability and use the definition. So kind of, but if you use the definition, then you write that this thing is equal to P of Px of 3 plus Px of 4 plus Px of 5 plus Px of 6. So suppose you don't have any software or any tables, just have a calculator. Then you could write it down like that, and after that it will be equal to e to the power of minus lambda, right? And kind of you can take it outside, minus 2.6. And after that here will be, okay, so will be lambda to the power of k, so 2.6 to the power of 3 divided by 3 factorial plus 2.6 to the power of 4 divided by 4 factorial plus 2.6 to the power of 5 divided by 5 factorial plus 2 to power 6 to the power of 6 divided by 6 factorial. 2.6, right? So this is kind of, well, so one of these methods will work. Right? And well, kind of if you calculate it, so let me see what it is. So it gives you around 46% or something like that, 46.44%. Right? Well, so this is kind of mechanical, just kind of, well, kind of as usual with all these distributions. So, right, so I'm sure that this is possible also do in Python, just you'll need to check out what's the distribution. So another kind of the more interesting question may be something like that. So what is the probability? What is the probability? What is the probability to have less than 10 accidents in six months, in a half year. And so now kind of this is a, well, kind of a different question. The question was, we are given information about the number of accidents in every month. Right? So the average number of accidents is 2.6 in every month. Here the question about a half of year. Right? And well, kind of in this case, we know that we have 6 random variables. So x1, x2, so this is x1, x2, x3, x4, x5, and x6. So kind of, so and say x3 is the number of accidents in year, sorry, not in year, in month 3. Month 3. Right, and what's very interesting in X, which is the sum of these probabilities. Right? And so, well, in principle, we know that expectation of X is equal to the sum of its expectations. So x of 1 plus so on plus e of xx. So it's equal to 6 times 2.6. So kind of sum of the average number of accidents in a half of year is equal to 6 multiplied by the 2.6. Right? But in principle, it's not clear. What about kind of what's the distribution of X? Well, it's kind of, but well, it's not immediately clear maybe, but intuitively it's clear that it still will be Poisson distribution, right? So intuitively it's clear, and it's also can be, it's possible to prove it rigorously, that if you have a sum, this is a kind of a theorem which says that you have a that you have a Poisson random variables and they're independent, then the sum of these Poisson random variables gives you another Poisson random variables. Right? So, so this is another property of Poisson random variables, sum of independent Poisson random variables. Again, we will need to kind of to some more information about independent random variables will kind of to prove it. But in principle, we can just kind of say that this is true. Sum of independent Poisson random variables is Poisson random variable. And again, so intuitively, absolutely clear that this is true. It's just the same kind of experiment, but instead of 1 month, you have a 6 months. And so the only thing that you'll need to figure out is what's the average number of accidents. And you figure out that this is equal 6 times 2.6. So the conclusion that X is Poisson in this case, but its parameter lambda is equal not 2.6, but 6.6 multiplied by 2.6. So now if you want to calculate what's the probability that X is smaller or equal than 10, then okay, so just apply this Poisson distribution, right? So it will be, say, kind of in terms of R, it will be P Poisson, so it's cumulative distribution function, P Poisson evaluated for at 10 with the lambda is equal to 6.26. So you know that kind of in R you can skip actually this lambda is equal to 6.26 and just write 6.26. But for clearness, you can also kind of say this is a named argument kind of. So if you kind of mix, if you write the named arguments in a different order, it still will be kind of possible. The program still can evaluate it in the right order. Okay, so let's see if I calculated it. No, I calculated only here is that it's equal, right? So if you want to calculate so that it's equal, you don't need any software. So if probability of X equal to 10, then you just need to, you write that E minus 6 times 2.6. Here's a lambda again, 6 multiplied by 2.6 to the power of 10 divided by 10 factorial. Right, so this is kind of, so this is, I don't know what is it kind of, but this is kind of, this is easy to evaluate. So this is equal to, this is equal to 3.95. Okay, maybe just maybe just let us look in one example of a calculation in R. So maybe let me stop sharing here and for a second and share the screen on the computer. Okay, so if we open R, Data Studio, then we have here and I type down, say, P Poisson, right? Then you can see that it gives the well, hint how to use it. So it says that you'll need to write Q, which is in this case will be equal 10. Right? Then after that you'll need to write lambda. So in principle you don't need to write lambda is equal to something. It's just kind of for clearness. Right? So you can write, so this is Q10, and after that you can either write just 6 multiplied by 2.6. Right? So gives you this, it's around 9.2%, right? Or in principle, if you kind of, well, you can also write something like that. And so it also gives you this answer. So this is just a named argument. All right, so let me see if it's all well, and if you kind of, so for PMF, right? So just kind of let us use once the PMF. So for PMF, we would write something like a D Poisson, right? And after that, this is again 10, and here's 6 multiplied by 2.6, and gives you this 3.9%, around 3. About 4% for having for probability to have exactly 10 accidents. Right, so okay, so let me see. Okay, so another thing to say about the Poisson distribution, right? And this is a kind of Poisson approximation to the binomial. Right? So Poisson approximation.
Just switch back to your tab.
Say it again.
You have to switch back to your tablet.
Yeah, so yeah, thank you. All right. Okay, so yeah, it's not, it takes more time to do it.
Sir?
Yep.
I have a question.
Yeah.
How would we've been doing all these questions with like software and stuff. How would we do this sort of thing on the exam? Do we just not get that kind of question?
Have difficulty hearing you.
Oh, I'm sorry. Do you mind if I just write it?
Okay. Okay, so there was a problem with internet. So what was the question again?
I wrote it in the chat. So.
In the chat? I don't see it. It might be that the chat cleared when you kind of, maybe kind of, can you type it again? No, on the exam, no, kind of, you wouldn't do it. It just kind of, this is just a question for, just for your information. Right? So mostly kind of, there are two things which I do in lectures, but which I will not ask you in the exam. So one thing is a proof. One thing is proofs. Right? So I will not ask you to do proofs in the exam. Right? So this is one thing. But kind of when you are saying something like which is requires explanation why it's true, then kind of I just cannot avoid using proofs just to explain why it's true. Right? Second thing which I will not ask you to do is this using the software in the exam. So, well, in principle, it could be done, but it will need kind of, well, kind of more advanced questions maybe about, well, the software. So kind of, so I'll try, in principle, I'll try to avoid the questions which will, which would not be able, which you would not be able to do using a calculator. So in this particular case, I could ask you to um, do the PMF, but all right, can you hear me? Can you hear me?
Yes.
Okay. So looks like, well, my internet connection is unstable, so looks as a good time to make a break. And maybe it will improve after the break. All right. So 5 minutes break. Right, so question. Professor, will the text will be open book, or should we spend time memorizing each of the PMF expectation and variances of this? You should spend the time memorizing each of these PMF expectation and variance of all these different random variables. So it's closed books. So, yep. Unfortunately. Yes. So, PMF, maybe you shouldn't, but definitely you should do it for binomial, for geometric, right, and for Poisson. Right? So this is definitely should be kind of done for these variables, because this is a, you need to know this. For all others, it's kind of, all others is the negative binomial for which you can calculate everything, because it's a sum of the geometric random variables. You don't need to know maybe kind of a, essentially you need to know all of them for this particular example. In general, in life, you'll need only for binomial, geometric, and Poisson. Yeah, but for this example, you should memorize these things. And kind of this is maybe kind of a homework gives an impression that it's all about kind of, it's a huge amount of material about this named random variables. But in principle, exam will have just maybe a couple of questions about them, just kind of one of these distributions. Right? And most of the questions will be about other things like PMF, CDF, right? So calculation of a conditional distribution, so calculation of the, according to the Bayes formula. So there is an impression that there are kind of huge number of named random variables, but the exam will be just a small portion of the exam. So you can look at how it was done in the previous version, and usually I think that it was a couple of equations, only a couple of equations on this thing. Are we going to be reviewing for the exam on Friday in about the calculators? So no, I'm not going to review this. So nope. So again, so kind of, I just kind of can say kind of immediately kind of, so let me kind of maybe start there. If you have a question, so why not to address it right now? So let me kind of look at the book and so here's the book. Right, so and here's the table of contents. Right. And so, and if you look at this chapter 2, so now kind of 2.5 and 2.6 is essentially about the kind of how to calculate these probabilities like the cards, right? Kind of combinatorial probabilities. So kind of something like about hands of the cards or something like that. And so now after that, conditional probability and independence of events, two laws of probabilities, and somewhere here is law of total probability. So essentially 2.7. So 2.77 basically says that you know what is the conditional probability and how to calculate it. Right? And independence events. So independence events in the homework, there was something like a problem about kind of, there was A, B, C, and you should calculate everything, which if A independent, you should be able to calculate everything which is kind of can be expressed in terms of A and B and C. Right? So there was a problem in the homework about this, right? Including the conditional probability. So it's about this one. Right? Now with two laws of the probabilities, and essentially the law of total probability and bias rule. So there was a bunch of problems about this. Right? So kind of this will be. So you can see here 3 kind of things: combinatorial probability, then another one is the ability to calculate the probabilities if you have a bunch of independent events and you mix them somehow. Right? Another one is so this is essentially chapter 2, effectively. Right? So now, if you look at the chapter 3, right? Then if you look at the chapter 3, then you'd have a PMF, CDF, so you need to know what is it and how to calculate the PMF and CDF, how to calculate CDF from how to calculate PMF from CDF. Right? Then expected value of a random variable of a random event. And well, kind of maybe here in the book, it doesn't have a, I don't see the variance. I covered variance in the lecture notes. So maybe kind of you need to know about the variance, and this is actually in the lecture notes. Right? So you should be able to calculate the variance if you're given a PMF. Right? So now after that, the bunch of these named random variables, which is kind of a couple of the problems, we'll cover one of them. And finally, there will be moment generating function, which I kind of planned to start today. So I hope that I will still be able to do it. Right? So, but I will cover it either today or kind of on Friday. And there will be a problem about moment generating function. Okay, so this is it. So we will not cover 310 probability generating function. We will not cover, I think, it at all. And we will cover 311 a little bit later in the kind of after the exam. Okay, so now the question about calculators. Well, you should be, yeah, the calculators are allowed. What kind of a calculator? Well, kind of scientific calculators. Well, okay, so yeah.
Okay, thank you, Professor.
Yeah. Okay, so okay, so now let me try to start again the sharing the screen. Hope well that it will be here. Stop share. Right, so now start broadcast. Now. Okay, so this is essentially Poisson approximation to binomial. What is going on? Cannot. Okay. Okay. Poisson approximation. To binomial. But it's kind of, so this basically says we use binomial distribution to calculate the Poisson distribution as a limit. Right? So in particular, it means that if the binomial distribution have n, large n and small p, then you can use a Poisson distribution to approximate the binomial. So if n is large and p is small, and maybe the book says something about this, so kind of, well, kind of something less than 5% may be small. Right? So kind of this is a little bit unclear. And well, lambda, which is NP, is small. So something like a smaller than equal than 7. I think the book says that this is smaller than equal than 7. Right? Then Poisson PMF, so Px of k is a good approximation for binomial binomial PMF. And so, and maybe kind of it's an example, and actually in example we kind of look at the fact that binomial is also can be used as approximation. So in this example, we look at the situation and we'll have a 1,000. So maybe it's too much, but kind of let us look at 10,000. Yeah, it's too much here. Kind of 10,000 students in a college. And so here we'll look at the kind of a situation with a small p. Right? So 3% of students are vegetarian. Right? So now if you look at the sample, so select 100 students at random. So and the question is, what's the probability that sample have at least 5 vegetarians. And so now if you look at this problem, then well, kind of the most straightforward kind of thing is that this is actually hypergeometric distribution. So the exact distribution is a hypergeometric distribution. Right? So the parameters here, so n is the population size is equal to 10,000. Right? After that, you say how many were marked students. So marked students are vegetarians, and it's 3% of this thing. And so 3% from 10,000, it's 300, right? So it's 0.03 multiplied by n, so it's equal to 300. Right? So ANN is equal to 100 here. So this is a sample size. So this is the parameters, and if you want to calculate that the probability of x is smaller than or equal than 5, then you calculate that kind of it's equal to px of 1, sorry, px of 0 plus px of 1 plus so on plus px of 5. So this will be kind of okay. So in every kind of these probabilities will be kind of denominator, right? Remember, kind of denominator is how many possible ways to choose 100 students out of the 10,000. Right? So kind of in every of these probabilities will be this denominator, but after that, so now what's the first one? So it's probability that there are 0 in this choice, there are 0 vegetarians. So 0 kind of out of 300. So this is the number of choices of the vegetarians. Right? So 0, 300. And here you need to choose all others 100 in the sample from the remaining kind of population, which will be kind of 10,000 minus 300. Okay, so this is the first probability. If you look at the second probability, it will be 300. You will select one of these 300 vegetarians, or 10,000 minus 300. It's all others, and you select 99 of the other people, and so on. Kind of you calculate it, and finally will be final possibility for this px of 5. It will be we select all 5 vegetarians for 300. Right, multiplied by 10,000 minus 300, so non-vegetarians, and you need to select 95 of them. And so now this is the kind of exact kind of calculation. If it's random, kind of everything, right? So, but after that you're saying, so in this case you have a huge population, right? So 10,000, and n is relatively small. It's 100. So sample size is small relatively to the population size. And so what you'll do in this case, you'll say, okay, so that means that this is sampling without replacing, right? So it's almost the same as sampling with replacement. So it's actually almost independent. There is almost independent. There is almost independence here. If you select one student and you found that this is kind of non-vegetarian, then it almost doesn't change the chances that the next one will be vegetarian or not vegetarian, right? So so everything here is large, kind of. So n is large, and small is large, which is, I think, this important thing. So n and small large, right? So you can use a binomial approximation, because n is much larger than n small. So this sign is just means much larger. Okay, so, and this is okay. So in this case, you ignore the kind of what's the n. You just say that the sample size is equal to 100 and p is equal to 0, 0, 3. Okay, so you're just saying that if you look at the student in this sample, the probability that the first student is vegetarian is 3%. Right? So the probability that second student in the sample is also 3%, and so on. Right? So kind of this is a kind of parameters of this binomial distribution. Right? So you count the number of vegetarians as the same as asking everyone, are you vegetarian? If he says yes, this is success. Kind of this happens with 3% probability. Right? So binomial experiment. Right? So you can find out that probability that x is smaller than equal than 5, and in this case will be calculation. In principle, it will be you need to get 0, kind of it's again a sum, like here it's the same sum, px of 0, px of 1 plus px of 5, but different formulas for px of 0, px of 1, and px of 5. So the first formula will be 0 out of 100 multiplied by 0, 0, 3. This is p to the power of 0, 1 minus 0, 0, 3 to the power of so what's the question? Why is it less than 5? We want at least 5 vegetarian. You're right. Yeah, you're right. Yeah. I'm calculating opposite thing, and even incorrect opposite thing.
Yeah, okay. All right. I have a better understanding.
Yeah. So let me kind of change the question, because I don't want to kind of at most. Yeah. So kind of, yeah.
Thank you.
Yeah. Thank you for the question. Yeah, this is actually incorrect that I'm doing here. So let me change the question. At most. You're absolutely right. So if I wanted at least, then I would have wanted to calculate p of x greater than equal than 5, and I would need to calculate something like 1 minus p of x smaller than equal than 4. Right? So this is a side, right? If at least. So what I'm doing here, I already wrote too much to change everything, right? So let me change the equation. All right, it's a very good question, yeah. At most 5 vegetarians, at least actually in the lectures notes, but I'm not looking at it very attentively. And so now here's 100 minus 0, right? And so on. So 100, 1 out of 100, 1 is a kind of vegetarian, 1 of 100 multiplied by 0, 0, 3 to the power of 1, 1 minus 0, 0, 3 to the power of 100 minus 1. So 100 minus 1 plus so on. Here's 105, 0, 0, 3 to the power of 5, 1 minus 0, 0, 3 to the power of 100 minus 5. Right? And this is a binomial approximation. You can never do it, or kind of in both of these cases, you could use a much easier way, and say in the first case you could say something like a p hyper with parameter 5, and so what would be here? 300, 110,000 minus 300, and p no, and n, so 100. So we should look it up in the help, so if it's right kind of order of the parameters. And here you would write something like a p binomial 5, then n, which is 100 here, sample size, and p, which is 0, 0, 3. Okay, so this is binomial approximation. But to binomial approximation, you can also kind of, you can notice that here is actually 100 is pretty large. 0, 0, 3 probability is pretty small. So p 0, 0, 3, it's small, kind of n is equal to 100 is large. So if you calculate what's the average number of vegetarians in your sample, so lambda and p is equal to 3, then it's smaller than 7. So according to our book, we can use also Poisson approximation. And the formula becomes simpler in this case, Poisson approximation. So Poisson approximation just says that in this case, probability that x smaller than or equal than 5 is equal to right, so e to the power of minus 3, right? And here's okay, so in this case 3 to the power, so the first one will be 3 to the power of 0. So again, we are summing PMF. So 0 all right, everyone back?
Yeah, we can hear you now.
You can hear me, right?
Yeah.
Okay, good. So today is something like happens with internet, at least at our department. Okay, so 3 to the power of 0, not 3, well, yeah, 3. So lambda is 3 here. Right? So on average, 3 people in the sample divided by 0 factorial. So this is essentially 1. Right? So e to the power of n plus e minus 3. Here's 3 to the power of 1 divided by 1 factorial, and so on, plus e minus 3. Here's 3 to the power of 5 divided by 5 factorial. Right? Or alternatively, again, so from the point of view, kind of, if you have a computer, it doesn't really matter kind of which approximation you use. From the point of view of computer, we'll write p Poisson, and here write the 5, right, the number at which you can calculate it, and the parameter, so lambda equal to 3. So that's it. And kind of the point is that they are not very different. So again, so maybe it becomes a little bit part of all right, back. Okay, so yeah. All right, so okay, so but maybe it's a part of the past because now you kind of calculate all of them just by kind of entering things in the software. But in theoretical analysis, it's often useful kind of that fact that you can use something simple, Poisson approximation considered simple, instead of a binomial. And binomial is definitely simpler than hypergeometric distribution. Right? Okay, so this is what is about this approximations. And so now, well, at least I want to start something like which is called moment generating function and moments. So this is the next topic, moments and moment generating function. Generating function. So far we looked at kind of on the two characteristics of a random variable. So far, we know that the random variable has expected value, right? And so e of x, and it has a variance, right? Which either you can write it's either e of an expected value often denoted mu, right? So variance is expectation of x minus mu squared, right? Or there is a formula which says that this is the same thing as expectation of x squared minus mu squared. And so these are two kind of characteristics of the random variable that we studied. So if you have a random variable, we can summarize what we know about it. We say, well, the expected value, so average value of this random variable is mu. And so the variance, kind of how it fluctuates around this average value, well, it's given by this thing, and it's always often called sigma squared. And so and kind of there is also STD, but this is just a square root of a variance. So square root of a variance, so it's not really different thing. So sigma. Now it turns out that sometimes it's not enough. Kind of sometimes you look at the random variable and says you want to distinguish between the random variable which is always between -1 and 1, and that's it. And the random variable which is between -1 and 1 often kind of, so this is random variable x1, but sometimes it have a deviation, large deviations. Okay? So x1 always between -1 and 1, so +1. And this x2 sometimes have large deviations, say to the right, never to the left, kind of something like that. So you want to kind of characterize, so you can describe, and you can actually make these two variables have a equal expectation and equal variance. Right? So it is possible a little bit shift the mass of that expectation will be, it is possible to make that they have the same expectation and variance, because this large deviation happen very rarely. Okay? So it is possible to make x1 and x2 have the same mu and sigma. So it turns out that in the statistical practice, the people found that they need a little bit more kind of an expectation, expected value, and the variance. And they invented two measures which is called skewness and kurtosis for this. kind of, but if you have these two measures, it's always interesting to have a more kind of general theory, and so more general theory about the moments. So kind of when you want to kind of, well, we'll have a two additional measures, so no, why not to define many of them? So to distinguish x1 and x2 in these cases, people invented moments of random variables. Right? And so what is the moment of random variables? So kth moment of a random variable, x is, by definition, it's mu k, it's equal to expectation of x to the power of k. That's it. And so if you want to figure out what is kind of in the case of a discrete random variable, then you can write that this is just a sum of all possible values of x to the power of k, and here's px of x. So kind of this is general definition which works always, including the continuous random variable. This is kind of works for the discrete random variables. And so, well, this is definition, right? Also, there is a kind of, so what's the examples, right? So now, say mu1 is equal to e of x. So it's just expected value. So this is in agreement with our what we did before, value. Right, mu2 is equal to e of x squared. Right, so, and now kind of, you can write it down as a variance of x plus e of x squared. Right? So because variance of x is equal to ex squared, variance of x equal to e of x squared, variance of x is equal to e of x squared minus e of x squared. Right? So if you kind of modify this formula, you'll get this thing. So they are closely related, so you can write that this is sigma squared plus mu squared. Okay, so this is the second moment. And you can also define third moment, e of x cubed. Fourth moment, e of x fourth, and so on. Right? So now, but in the practice, okay, so this is the moments. This is what is the moments. In practice, often people use centered moments. So another one is a centered moments. And so it's just kind of, what is it? It's mu k centered. Right? It's equal to expectation of x minus mu. So you subtract the mean value, and after that take the power of k, and that's it. So this is the definition. So in particular, if you look at the first centered moment, then it's equal to 0, right? So you kind of, so it's equal to e of x minus mu, right? But it's equal to e of x minus expectation of mu, so minus mu, so it's equal to 0. So it's not really a very interesting moment, right? So the second moment, second centered moment, is equal to e of x minus mu squared, and well, this is by definition sigma squared. So second centered moment is a variance. Okay, so this is a variance. Right? And now interesting thing happens when you look at the next one. So it's mu2 mu 3 of c, which is equal to expectation of x minus mu to the power of 3. Right? Right? So, okay, so this is a third moment, third certain moment, and mu 4 of c is equal to e of x minus mu to the power of 4. And so now one bad thing about that, right, and this is related, so related to the thing that we subtracted mu. So just because we don't really, at this moment, kind of, we don't really want to look at the expected value. And we want to modify the random variable such that we have the same expected value and the same variance. So here we have not yet modified that it have the same variance. And so this is centered moment, but it's not yet kind of what the statistician use. So statistician would also divide these measures by the variance. So we would say, so let's look at mu 3c and let us divide by the kind of such that if you scale this variable, it will have the same measure. So for this, you will need to divide by standard deviation to the power of 3, right? Sigma to the power of 3. Because if you scale this x and you multiply it by something, then this third moment, it will scale by the third power of whatever you multiply it. And so you divide by sigma of 3 such that it will have no effect. So this measure is called skewness. Skewness of random variable x. And mu 4 centered divided by sigma 4 is called the kurtosis. Kurtosis of random variable x. So these are two methods which is kind of used in statistics to kind of quantify if there is something beyond the standard deviation. So if you look at our previous example, for example, so right, so we have a random variable which was between -1 and 1. Right, and say kind of uniformly, something like a more or less uniformly distributed between -1 and 1. So the probability that you'll get anything here is something like a kind of equally probable. And so x1 and x2, it would have something like between -1 and 1, but very rare, occasionally have a large deviation to the right. And so what we observed that this sigma, so this skewness of x2 would be greater than the skewness of x1. And which was just say that it deviates to the right. Right? So it's not deviates to the both sides, it deviates more to the right. And the kurtosis would be also greater. It's just kind of kurtosis just detect that there are large deviations. Kurtosis of x2 would be greater than kurtosis of x1. Okay, so this is how you could detect. Well, if the deviation could be both to the left and to the right, then the skewness would be the same for these two variables, would be about equal to 0. All right, so these are moments. Right, so this is a kind of something like a practical, but in kind of now we are going to maybe I'll write the definition right now. Something which is called moment generating function. And we will do it more function. Right, so moments, it's something like which came from the very practical questions. Moment generating function, it's a theoretical tool. It's not really it's used for two reasons. So first of all, it's used to calculate moments, moments theoretically. So moments in practice, they are calculated well using observations. So they are estimated from the observation. But theoretically, they are calculating kind of you need to calculate with expectations, right? Always expectation. This is not easy if with a high moments like fourth or third or higher. So you need some tool, theoretical tool, and this theoretical tool is given by a moment generating function, right? And so this is first one, and second used to prove limit theorems. So this is a more like a theoretical tools. So kind of you still need to know about this, right? So kind of this is very useful if you go to an advanced probability theory, but kind of it's not immediately clear why kind of it's very relevant, kind of, right? So it's a more advanced tool, and so that's why kind of it's in the end of this chapter. And so again, so let me kind of just state the definition, and we'll start from this below. So the definition is this thing. So this is m of x of t, and so it's by definition it's equal to expectation of e t of x. So this is the definition of this thing. And so now if you want kind of to, well, kind of, right? So if you specialize for discrete random variable, then you can write it as sum for all possible values of x, and here will be e t of x, and here's p x of x. And so now this t is a variable, right? So variable. It's not random variable, it's just kind of, this is a function, it depends on t. And so this kind of, so you can calculate what is mx of 0.1, you can calculate what is mx of minus 0.1. So right, so what you need, you take this 0.1, plug in into this formula, right, and calculate what's this sum. Right? So kind of this is kind of what this t means. All right, so maybe kind of goodness, so we are running over time, so let us stop now. Next time we will talk about more about this moment generating function. Kind of, this is our program for Friday. All right.
Thank you.
Yeah.
Thank you.
May I ask
Thank
a
you.
question?
Yes.
So going back to where we were calculating the Poisson approximation, I was wondering why you were using the binomial distribution and not the binomial coefficient. Yeah, like at the top of the page right now.
Well, binomial coefficient, well, it's a coefficient, so it's just a it's not a distribution, right? So it's just well, number of ways select k items out of n items. Right? So now kind of if you want to calculate the probability, then you'll need a distribution.
Okay, so when you're doing like the probability of getting 0 or the probability of getting one person, you need to use the distribution instead of just the binomial coefficient. I thought that you could put the binomial coefficient and you would get a probability as long as it was over another binomial coefficient.
No.
Okay.
No, it's just kind of in this. So yes. So in some situation you could have a probability which is a ratio of two binomial coefficients.
Right.
Right. But in this case, kind of, you have a specific experiment, right? So specific situation, right? So you have a so this is kind of, this example is a description of this experiment. Okay, so it's 1,000 students in a college and 3% of students are vegetarians. Right? And you select 100 students at random. So it's a description of a specific experiment. And so at this moment you'll need to think about, okay, so this is experiment. What is the random variable kind of, and there is a question. So the random variable here is that the number of the vegetarians in the sample. At this moment you'll need to say, okay, so this is the experiment. This is a random variable. So this is kind of what you observe after you did this experiment. What's the distribution, right? And so now we have a pretty big collection of the distribution. So it becomes a hard question in some sense. So you have many distributions. You need to ask the question, what's the distribution? What's the right distribution apply in this case? Right? And well, kind of you look at this, and the most closely this description matches the description of a hypergeometric experiment. Right? Because you have a kind of, you know that there is a large population of the students. You take a sample from the large population of the student. You know the parameters of this thing. So you're saying this looks like a description of the experiment which gives you a hypergeometric distribution. Right? Okay, so and well, the first thing we did, well, you can calculate it. After that, you're saying, well, kind of, it's a kind of description of a hypergeometric distribution, but you can also describe it, well, it's a little bit, will be not right, but it looks very much like the description of a binomial experiment. Right? So it's like that if you look at the sample of people, and you kind of, you can describe it by asking the first person, are you vegetarian? He says yes. And you ask the next one, he says no. And the number of people in the sample, just the number of successes, number of yes answers in this experiment. So you give a little bit different description to this experiment. It's not quite correct because they're not independent. And if the 5 students in a row will say to you kind of, maybe kind of, yeah, so kind of 10 students in a row say to you that they are vegetarians, maybe slightly change the probability that the next ones will say that vegetarians, because, well, you know that now it's not 300 around vegetarians available, but 290. Right? So, but it's approximately binomial. Description of binomial experiment, so you say it's probably binomial random variable, and you know that's kind of, from the textbook, you know what's the distribution of a binomial random variable. Right? Right? So now after that you're saying, all right, okay, so, but it also looks like kind of, well, at this moment that's kind of, it's Poisson, it's here used as an approximation. You are saying, so this is a big sample, right? So 100. And so kind of, I think that 100 is about infinity, right? So kind of, and you're saying, then if it's kind of, if it's kind of, you look at like a counter kind of, so it's a big, very big sample, right? So n is very large. At p, the probability that I ask somebody and he says me that he's vegetarian is very small. Right? So it's like a description of a Poisson experiment, in which case kind of the number of trials is infinite and the probability of each of them is 0, but average is fixed lambda. This looks like Poisson. Right? So, and you can use a Poisson distribution to describe the same situation. So this is kind of what's going on in this example. So it's all about kind of what's the model, what's the random variable choose for this specific problem. And it's, it's usual question when the student asks me, so now we have a kind of 5 distributions. So this problem kind of on the exam, on somewhere else, it doesn't say to me what's the distribution. So which distribution I should use. Right? And it's exactly kind of about this. So you have a real situation, which distribution you should apply to this situation. So this is kind of this is the hardest question.
Yeah, it often is. I agree. Just a last follow-up question is, so the way you have your screen now, the probability of like the binomial approximation, it seems like on the bottom you're using the distribution, but on the top you're using the coefficient. or that's on the top it's the hypergeometric, and on the bottom it's the binomial approximation to the hypergeometric.
Yep.
Okay, that makes a lot more sense. Okay.
Yeah.
Okay.
Yeah, so this is a hypergeometric distribution, right? So every kind of term here is a hypergeometric distribution, and here's a binomial approximation. This is second way how you can do it, right? So here.
And that's okay. So all right.
And the last one that I did is Poisson approximation. So it's another kind of way to look at this situation, right? So.
But we're looking at the Poisson approximation distribution, correct?
So Poisson approximation means that instead of using binomial distribution, we use a Poisson distribution.
Right. Okay.
So approximation means, well, kind of that we will get the number which is similar. Well, I didn't do the calculation here because I a little bit switched the wording of the problem. In the lecture notes, where I actually asked the right question, right? At least 5 vegetarians, I did the calculation for at least, right? And I found that the differences between these two free calculations. So you'll get one number here, right? So you'll get another number here, and you'll get another number for Poisson. When you do this calculation, you get 3 numbers. And the punchline, which I missed because I kind of missed the kind of this more, instead of at least, I started to calculate at most, right? And I don't have these numbers. But the punchline was with these 3 numbers are different in the third digits. In the third digit.
Right, but they're approximately the same.
They're approximately, they're different, but this difference is tiny. It's kind of less than, in the third digit after the dot. So the difference is in this particular case is tiny. So this is why it's approximation.
So would it be correct to use any of the 3 on an exam, or is?
Well, in this situation, yes, but kind of.
but not. Of course, not always.
But maybe kind of, So when the exam would happen, you probably will not be using something like a hypergeometric, because for hypergeometric distribution you need to know n, right? So if you don't, you will not be able to get it. Okay. So if you have an n, so suppose you have this thing, and instead of using hypergeometric, you calculate the thing using binomial approximation. So probably I will kind of subtract a little bit, but very small amount, right? So because, you could do it. You always kind of, the thing is that this is approximation, so it not always works well. So the binomial approximation works well if this is true, if n is much larger than n small, right? In this particular case, n is equal to 10,000 and n small is equal to 100, right? So n is much larger than n small. So the population itself is huge, the sample is small, right? So kind of in this case, the binomial approximation works well. Right, so assumptions are kind of satisfied. So when the Poisson approximation works well, it's when p is small, so this is very small, n is large, and lambda is kind of, not too large, so smaller than 7. So what will happen if you kind of use this approximation, but this is not true, so say p is not small or n is not sufficiently large, then you'll get a kind of, will be not so close to the true answer.
Okay.
And so you'll still get something probably not too far from the right, but kind of not right answer.
And when you say large and small, like small is
that's good question. I don't really know, kind of. I think that in the textbook says something about this. So I think it says something like that lambda should be smaller than 7 and n should be something like a greater than 30 something, but I don't remember it.
Okay.
And so p is also, maybe it says something about p, but I don't remember it. The textbook says something about this. So because in why I don't remember it, because in real situations it's usually clear that something is large.
Yeah.
Really in the borderline cases. So, but the rule of the thumb, yes, that lambda should be smaller than 7 and should be greater than 30. I'm not remember about p. Right? Maybe 5%. I'm not sure about the p.
Yeah, it would make sense that you from lambda you can derive p if you have n.
Maybe, yeah.
All right. That was really helpful. Thank you so much.
Okay. Thank you.
Okay. I'm gonna go. Have a great day.